This is AQA A-Level Chemistry. It's Aromatic Chemistry, a Year 13 topic, and this is part 2 of 2. In this particular video, we're going to take a look at some of the mechanisms and reactions of arenes. That's aromatic chemistry, aromatic compounds. As always, I'm going to recommend you pause, have a go at the activities for yourselves, and then when you are ready, you can review. We're going to jump straight in with some nomenclature. And the nomenclature on aromatic compounds, on benzene, has got one or two peculiarities that we'll see as we go through these examples. We're going to start on the top left, have a go at naming it, and see if you're on the right lines. So what we've got here is a benzene ring. We've got the circle in the middle that characterises it, and we have got a methyl group coming off it. Now, it doesn't matter where it comes off because there's only one of them. So the name for that one is methylbenzene. I've then numbered number 2 below. Have a go at naming that one. So in this case, it's benzene again. It's got 2 chloros coming off there, so that's dichloro. And the numbers, if I were to number them, would be 1, 2, 3, 4. Conversely, if I number from this end, 1, 2, 3, 4. Either way, the name is 1,4-dichlorobenzene. So let's move on to the one that I've numbered as number 3. This is a skeletal formula, so obviously the sticks, that implies there's a CH3 on the end of it. So I've got 3 methyl groups coming off my benzene, so that's going to be trichlorobenzene. In terms of the numbering, you've got to be very careful here. It's not a matter of going around clockwise, you're looking for the lowest possible numbers. So I'm going to number from here, and I've got 1, I'm going to go anti-clockwise, so I've got 1, 2, and 4. 1, 2, 4, trichlorobenzene. If you'd done 1, 3, 4, that would therefore be incorrect. You've got number 4 labelled at the top. Have a go at naming this one. And for number 4, this time we've still got 3 halo groups coming off there. We've got 2 chloros, that's dichloro, 1 bromo, which is a bromo. And the lowest possible numbering that you're going to have is once again going to be 1, 2, 4. So it's definitely a 1, 2 for the dichloro. It's a 4 for the bromo. But we've then got to remember that prefixes are put in alphabetically. So it becomes 4 bromo, 1, 2, dichlorobenzene. Have a go at number 5 now that I've labelled just below. And this is one of the peculiarities because benzene can be a suffix, but it can also be a prefix. And you have got to learn where those prefixes are used. This is one example of it. This is an alcohol, so it ends in ol, but the phenyl group that's coming off it, the C6H5, becomes phenyl ethanol. Now that commonly gets shortened to phenol. I've done number 6 here as well. You can see down at the bottom, and we're back to benzene as a suffix. You have to know that NO2 is a nitro group. We actually do a mechanism where we make this, and that becomes nitrobenzene. And we've got number 7 just above there. Have a go at naming that. Slightly more straightforward than we have seen. So there are 3 methyl groups. It's trimethyl, and that therefore means that we are going to have trimethylbenzene, and the numbering of these, because they're all next to each other, is going to be 1, 2, 3 trimethylbenzene. The final one is another one of those quirks, those anomalies. We have got the benzene group here. We've got a C double bond O, in case that's not clear, and a CH3. So have a go at naming that one. So there is something quite odd about this name. First of all, we have got a phenyl group coming off. We're using the prefix rather than the suffix. But we've also got something that you don't ever really come across in any other circumstance. Because if you've done work on aldehydes and ketones, you will know that ethanone cannot exist because the double bond has to be in the middle of a carbon chain. In this particular case, the double bond O is on a carbon in the middle of the carbon chain, and the phenyl forms a part of that carbon chain. So it's that one example where ethanone will be a valid part of the name. And we're actually going to take a look at a mechanism to make this one as well later on. Okay, in terms of reactivity, quite a lot of information here. In general, we are looking at substitution mechanisms when we react them. And as it says on here, they are electrophilic substitution. Now, in a moment, I'm going to suggest you take a read through this. I will go through some of the key points, but then have a go at doing the mechanism. If this is a revision, it's a great chance for you to see how well you're doing. If not, if it's the first time you're looking at it, it's a good opportunity to try to work out why what's happening in the mechanism is happening. So the ring is high electron density. It's 6 delocalized electrons, and therefore it's susceptible to attack by electrophiles. The aromatic ring itself is very stable. You actually need to put a lot of energy in to break it. You can also combust benzene, and you would make carbon dioxide and water, although you're actually likely to get a very smoky flame. And that's because you have got, you've got a very high carbon content within benzene. There's a high carbon percentage. So you need a huge amount of oxygen to combust it. So you'll see a smoky flame. But back to this, the aromatic ring is very stable. You need to put energy in before it can be destroyed. It does mean that, generally speaking, apart from the combustion I just spoke of, the carbon ring, that stability, sorry, the delocalized ring of electrons within the carbon ring is likely to survive any reaction that takes place. So when we're looking at mechanisms, we're dealing with electrophilic substitution. So if we were to use an electrophile E+ and a benzene ring, what do you think that mechanism would look like? Well, let's start off by drawing my benzene ring and my E+. And if I were to draw a curly arrow on here going from electron rich to electron deficient, it of course makes sense. It's going to go from the delocalized ring of electrons, very electron rich, and it's going to go towards the more electron deficient, in this case, the E+. Now that means I'm forming a bond, and that bond will look like this. It's actually really important that when you draw them, we show the same structure right the way through. And what I mean by that is because my curly arrow has passed through this part of the benzene ring, my E would have to be added on this carbon or this carbon for it to be valid and correct. It also means that I now have to draw the H coming off there. That's because it becomes an important part of the progress of the mechanism from this point on. But I'm not done yet, because I now don't have 6 electrons in the delocalized ring. I only have 5. So my delocalized ring is broken. I represent that by showing a broken ring, which you can see is coming as far as, but no further, than the carbons that are adjacent to the one that the E has been added to. And I'm remembering to add my positive charge within that broken ring. That then allows me to do the final part of this mechanism, which is whereby we lose an H. The electrons in the CH bond move back in to help regenerate the ring. That then leaves me with my E that substituted the H that was there, and I've now got the H plus coming off. My delocalized ring has been reformed. Electrophilic substitution. Now, one of the specific examples that you need to look at for this is the nitration of benzene. I want you to have a think about what my electrophile would look like to get nitration of benzene. That's an NO2 replacing the H, and then have a go at doing the mechanism. So the benzene looks like this, and my electrophile is going to have to be NO2+, because I need that NO2 to go on there. The mechanism then follows exactly the same pattern as we have just seen. I have the first arrow going from my electron-rich delocalized ring towards the NO2+, electron-rich to electron-deficient. Just as I did with my E, I have now got my NO2 connected to my carbon ring. I'm now showing my H, and I have got my broken delocalized ring with the positive charge. And that then means that the CH bond can be broken, those electrons can move back in to regenerate the ring, and I've made H plus as a secondary product, but I've made my nitrobenzene. A big extra part of this question is you need to know how the NO2 plus is generated. We do it by reacting concentrated sulfuric and concentrated nitric acid. They are both in bold because if you miss one of them, you lose marks. For example, if you were asked in an exam and you wrote concentrated sulfuric and nitric acid, you would get 1 of 2 marks. But what actually happens when we react them? Well, the H2SO4 will donate a proton and the HNO3 will accept a proton. So we get HSO4- and H2NO3+. The H2NO3+ is unstable, so that breaks down into H2O and NO2+, and we have got our electrophile. Now you can also see this alternatively as a one-step process, which I'm going to do in red. It simply combines those two equations. H2SO4 and HNO3, both concentrated, react to make HSO4-, H2O, and my NO2+ ion that can then attack my benzene. So what are they acting as? This is a neutralization reaction, or certainly it's an acid-base reaction. Well, the H2SO4 and the HNO3. The H2SO4 is a proton donor, making it an acid. My nitric acid is acting as a base. This might go against what your previous knowledge has been on acids and bases, but it will be covered in much more depth in the acids and bases topic in Year 13 chemistry if you haven't done it already. Now, the sulfuric acid is also acting as something else in this reaction. Let's have a think about what it could be and why. Well, remember that in the mechanism we're making H+ ions. We saw that in the general mechanism and in the nitration of benzene. The HSO4- ion can react with that H+, and in doing so, regenerates H2SO4. That means that the sulfuric acid is acting as a catalyst. These are all really important points to take on board. Now, often making nitrobenzene is a midpoint in the making of phenylamine, which we can see here. What I want you to do on this one is make sure you take on board the information. This is a reduction reaction where the NO2 becomes NH2. We can do that using iron or tin with moderately concentrated HCl. Alternatively, we can do it through hydrogenation, H2 with a nickel catalyst. I want you to have a go at balancing this equation. And it's important that you note that there's NO2 on the left, but there's H2O on the right. So I need 2 H2O. And that then means that I'm going to need 6 of the H in square brackets. You will have learnt in the carbonyls topic about using H to represent reducing agents. If you're unfamiliar with it, I do recommend you go back and take a look. A little bit of nomenclature here, or drawing based on nomenclature. 2,4,6-trinitromethylbenzene, also known as trinitrotoluene, which is shortened to TNT. How would you go about drawing the display formula for TNT? Well, here's my benzene ring. I've got my NO2 coming off. That's in the 1 position because that takes priority. So my 3 methyl groups go in the 2, the 4, and the 6 position. However, this is wrong. Think carefully about why it's wrong. It's to do with the fact that you need the display formula. And the display formula must show every single bond. So if I wanted to do that, I would need to show every CH bond and my N double bond O bonds as well. And I now have the correct display formula. We're going to finish off by taking a look at Friedel-Crafts reactions. This is another mechanism. Same mechanism again, but with different electrophiles. And we have got here ethanoyl, propanoyl, and butanoyl chlorides. And again, you learn about those within the carbonyl topic. So we can see here that actually I could take, for example, ethanoyl chloride here, and I can react it with AlCl3 to make this positive ion. If I do the same with propanoyl chloride, I end up losing the Cl and I make this acyl carbocations. And this is acylation of benzene. So, from beginning to end, including making the electrophile, can you propose a mechanism to show the reaction to form phenyl ethanone? Well, that means I'm going to need ethanoyl chloride, CH3COCl. If I react it with AlCl3, the catalyst, I make CH3CO+, my positive is on the carbon, that's quite important, and I've made AlCl4-. Now that means I've actually made my electrophile. I've got my positively charged carbon on here, and if I draw that out in this way, we can then follow the mechanism through exactly as we've seen it previously. My first arrow going from the delocalized ring of electrons to the positive carbon. I then draw my intermediate structure. I've got my broken delocalized ring. I've got my H now included because that's an important part of the mechanism. And I have got my COCH3 included. Now that then means that my CH bond can be broken. Those electrons move back in to reform the ring, and I have made my product. I've got my H+, and I've got my C6H5 COCH3. Phenyl ethanone that we spoke about earlier. Remember that little quirk in the naming. It is in the middle of the carbon chain. We can have ethanone in this circumstance. But we can also think about how AlCl3 is a catalyst, because the AlCl4- can react with the H+, making HCl and regenerating the AlCl3. There it is, the Friedel-Crafts catalyst. That takes us to the end of the aromatics topic and this video. Thank you for listening, and goodbye.